Welcome back again. Now we enter into chapter 3, high frequency behavior of electrical components. This chapter is divided into 4 modules. First we will look into the behavior of conductors, plain conductors in the form of wires, or it can be of different cross sections, round wire or rectangular wire, it does not matter what it is, or it can be plain sheets. Then we look into some of the electronic components that are called capacitors, inductors and resistors. These are the basic passive electronic components. And of course, these electronic components also has got wires in it in the form of component leads, where you solder these components into printed circuit boards. And so then you get a combination of conductors and this ideal capacitors, inductors and resistors. Then we look into mechanical switches, which are supposed to be switching off the current, on the current. So ideal mechanical switch commute between 0 voltage and certain finite voltage in 0 time, but of course there are no such ideal mechanical switches. Then the last module is some numerical exercises. So these we have an idealized version of these components in our mind, but we can see that these components are not behaving as we think it would under high frequencies. When the frequency is increasing, a lot of things are changing in the behavior of conductors and capacitors, inductors and resistors or switches or transformers. We will look into those. Now, before talking about conductors, I will try to illustrate what I mean to achieve in this chapter. Take a case of source. Okay, it has got some internal impedance, let us represented by R. So this source is connected to a load by a switch. Then you have certain resistance and inductance for the loads. So this source has a reference. So this is the symbol for the ground. This is grounded over here. We can have a capacitance across. Again, it is ground or reference. It is so. This is a kind of a circuit. This is R, L, and C. So in this circuit, we think of certain behavior for R, certain behavior for L and C, and by this we means that they are all at 0 volt, same voltage. But when you do this in practice, you have some sort of a track connecting all these grounds together, and that is made of a conductor. Similarly, all these components are connected together by conductors. So these conductors carry certain currents, and it can have certain voltages in it. So due to that, it is producing some electric fields and some magnetic fields. So associated with electric and magnetic fields and the currents. And since these are not ideal conductors, you can have some resistance, some inductance and some capacitance like that. So what we call as a plain conductor of 0 impedance is actually an impedance network under high frequencies, when frequency is increasing, not for DC. Even for DC you can have some resistance, of course. Then the capacitance also are not ideal. So, your real circuit under high frequency is much more complex than that we see over here. You can have potential difference between this point and this point because of the impedance of this conductor. So, it is these things that we are coming into by describing the non-ideal behavior of each of these components. So, the concepts developed here will be used in chapter 4 while talking about crosstalk and other interference coupling mechanism. So, let us go to the conductors. Especially we will introduce an important concept called skin effect. It kind of idealize, or it kind of state that under high frequencies the current density across the conductor is not uniform. So, for example, if you have a superconductor, since you cannot have any field penetration inside the conductor, all the currents will be confined to the surface because it is superconducting, conductivity is infinite theoretically. So, you cannot have any electric and magnetic fields inside the conductor. So, there cannot be any current inside or potential difference inside. So, all the currents are confined to the skin, but there are no real superconductors. All these conductors that we use are not superconductors and have finite conductivity like copper, iron or aluminum. With finite conductivity and under DC, the current distribution across the cross section is uniform. So, if you take a round conductor and if it carries a DC current, the current distribution is uniform. Say if we represent J max like this, so it will be a constant current distribution like a straight line, not a curved line that is shown over here. So, in a plate of thickness D, again it will be a straight line, not a curve like this. But what happens when conductors are subjected to high frequency, when a high frequency current is passing through this, then the magnetic fields tend to crowd or the currents tend to crowd along the surface of the conductor. So, you have maximum current density along the surface and the current density is reducing as you go deeper into the conductor. So, then you can define a condition like this. The skin depth delta is the distance over which the amplitude E0 into e to the power of minus alpha x of the wave decreases by 1 by E. That is alpha is the propagation constant that you have seen in chapter 2. If the wave amplitude is decreasing by 1 by E, that is about 1 by E is about 37%, then that distance is called the skin depth. So, if you substitute in this, you can see that skin depth is nothing but 1 by alpha is the attenuation constant. So, skin depth is 1 by attenuation constant, and for good conductors we have defined we know the attenuation constant, and skin depth is obtained as square root of 1 by pi f mu sigma, where f is the frequency, mu is the magnetic permeability and sigma is the conductivity of that metal. So, this is the relation for skin depth. So, inspection of this will show immediately some interesting properties of skin depth. For example, skin depth is decreasing with increasing frequency. That is, as frequencies increases, more and more currents are crowding around the surface. So, this is a cylindrical wire, round, in cross section. So, this is a vertical cross section like this. So, as the frequency is increasing, this becomes steeper even, sorry. So, it may be something like this, and as the frequency is increasing even further, you may come to a state in which most of the current is confined to the surface and the inner part of the conductor is not carrying any current. So, this is the reason why we have stranded conductors often when we carry high frequency currents, because stranded conductors are more efficient than a single solid conductors, because we do not use all the area of the conductor for carrying the current. Now, if you integrate for the current across 0 to d, the thickness and the current density, then you can get this expression. J0 is the initial current density minus x by delta. X is the distance along this axis. Then you will get I0 delta into 1 minus e to the power of minus d by delta. So, this will be the expression for skin depth and sorry, expression for the total current. And you can take a special case of conductors, round conductors, and do a calculation for high frequency resistance. R equal to L divided by sigma A. Sigma is the conductivity, area is the cross section. So, this is the formula for the resistance, and per meter DC resistance will become 1 by sigma pi r squared. That will be the per meter DC resistance. Now, the influence of skin effect is coming in this way, reduced cross sectional area, because as you go much higher in frequency here, this delta is much smaller, skin depth is much smaller compared to d. So, this becomes almost negligible, and almost all the current is confined to the surface. J0 delta times 1 will become the total current. So, they are confining to 1 skin depth deep. So, that is what we see over here. So, low frequency resistance is approximately equal to the DC resistance when R is far less than delta. When the radius is far greater than skin depth, and if it is confining to 1 skin depth depth, then high frequency resistance can be approximated as 1 over sigma, then area of this small section over here, small washer shaped section here, that is 2 pi r times delta. So, that will be this area. So, that will be the high frequency resistance. Now, we can see we can do a comparison of high frequency resistance to DC resistance for copper and iron wires. So, high frequency resistance is much higher than DC resistance, and if you take the ratio, you will see that the effect of skin depth is already coming at 10 hertz for very thick iron wire of 2 centimeter in diameter or 20 millimeter in diameter. Even at such low frequency, you have some effect of skin depth. So, for copper, already at 100 hertz of 2 centimeter diameter copper, you will have effect of skin depth. Say for example, at 10 kilohertz, already ion will have a high frequency resistance that is around 30 or 40 times the DC resistance. So, skin depth make a big difference in the resistance. For thin wires, the effect of skin depth happens at much lower, much higher frequencies. Say if you want to, if you decide that okay, you need a surface area for the conductor that is effectively equal to, let us say, 20 millimeter for copper of diameter, you can achieve the same cross-sectional area of 20 millimeter with diameter. So, pi r squared. So, that same area, cross-sectional area, you can achieve by stacking several conductors, small conductors together. That is standard construction. Then you will have to face the problem of skin effect only at 1 megahertz or so, instead of already at 100 hertz. So, this is a strong motivation for using standard conductors. Of course, another reason is the mechanical one. Standard conductors are very flexible compared to solid conductors. Now, another property of wires are inductance. Every wire will have inductance. Anything that carries a current or have set up a magnetic field around it will have some inductance. If you look at the literature, inductance concept is more confusing than resistance or even capacitance, because often inductance is in association with the return circuit, and often that is not very clear. For example, you have terms like internal inductance, external inductance, self-inductance, mutual inductance, loop inductance, partial inductance. So, there are several terms like this. And what are these? What are the differences between these various types of inductance? So, the next few slides we will devote time for this. Here we describe internal and external inductances. Say, suppose you have a reference and some current is carried by this conductor, and this current sets up a field inside this conductor. So, the whole flux is inside. You just ignore all the flux outside now. So, the flux inside linking with that current itself, that you can define an inductance. Inductance is defined as flux linkage divided by the current causing it. So, that is called the internal inductance. The flux is confined to the internal part of the conductor. For DC and for low frequencies, you can find that internal inductance is nothing but mu by 8 pi Henry per meter. That will be the internal inductance. And this will be for copper conductors, internal inductance will be mu by 8 pi will be around 50 nano Henry per meter. So, the internal inductance reduces with increasing frequency, because as you increase the frequency, you do not have that much flux linking with it, because the currents are more confined to the periphery. So, you can set up the equations and find that the inductance will be reducing with increasing frequency. So, internal inductance is not of a problem really for most conductors, because external inductance is much larger. So, external inductance is defined as the flux due to the current in this linking with this return circuit or reference. So, this flux divided by the current. or rate of change of this flux divided by rate of change of this current. So, that is external inductance. So, this will be much larger compared to the internal inductance. So, here there are some more details of finding the internal inductance is given here. So, this is radius r and this is x, let us say arbitrary value, and you get the total current by integrating from x is equal to 0 to r. All the current densities available here. So, if you take a ring at a distance x having a flux B like this, you see that for low frequencies the current in the wire can be assumed to be uniformly distributed, and the magnetic flux lines inside the circular conductor encloses only a portion of the total current, and that portion is pi x squared, proportional to pi x squared, this area, whereas total current is proportional to the area of pi r squared. So, you can take this ratio, and this is the portion of the magnetic flux inside linking with this current. Now, this we have seen. So, we get mu by 8 pi if you do the integration, and at high frequencies the current is concentrated in a thickness of delta at the surface, and the per unit length inductance is given by L internally equals mu delta by 4 pi r. This also you can set up from this figure, and integrating with appropriate limit you will get this value for r far greater than delta. So, internal inductance, explicitly writing it out delta, you see that it is reducing in proportion to the root of frequency. So, you can say that high frequency, the per unit length internal inductance decreases at a rate of 10 dB per decade. In the previous class you have seen what it means by dB. So, if you take the log of this, this is 1 by root f, then because even resistance you can express in terms of or impedance you can express in terms of dB. So, 20 log 1 by root f is f to the power of 1 by 2. So, 20 into 1 by 2 is 10. So, per 10 times increase in frequency you have 10 dB increase in inductance. So, that is the meaning of this equation. Now, effect of skin effect on the resistance and internal inductance of round wires. We have seen this that it is increasing 10 dB per decade. So, it is shown in the form of a curve here. The basic expressions you have seen. This is the expression 1 over delta. Delta is 1 by root f proportional to, so root f is coming on top. So, 10 dB per decade increase, and that is what we are seeing in this picture. So, this is written in terms of r by delta, the ratio r by delta. Then this is a 10 dB per decade decrease. That expression we have seen before, this expression, and you take r by delta, you plot it across it. So, that is coming, this is high frequency, f is coming here, Now, self and mutual inductances. Self inductance is defined like this. So, for example, you have some flux phi s that is marked over here, and you have certain current I A here. So, you take these circuits A and reference here like this. You take all the flux set up by I A between these two wires per meter, and that flux divided by the current I A, that is defined as self inductance. So, self inductance will also include the internal inductance of this wire. Internal inductance of the wires also will be included in self inductance. Now, in the mutual inductance, you take this current, you see how much it will, how much of the flux will couple with the circuit B. So, that one, that flux, mutual flux divided by this current is called mutual inductance, henries per meter. So, self and mutual inductance is different from internal and external inductance. So, there are important differences. So, do not confuse between them. Internal inductance is part of the self inductance. So, here we have seen the external inductance. So, this external inductance of this wire plus this internal inductance together will form the self inductance, and this is mutual inductance, interaction of the current in one circuit with the other circuit. So, this is mutual inductance. So, loop and partial inductances. So, these concepts are not very common, but sometimes they are used. Say for example, if you have a loop like this with sides P, Q, R, S carrying some current, we call off a loop inductance. So, you take the circulating current and the magnetic flux confined by this loop. So, the ratio is defined as the inductance, but sometimes the loop can be of irregular shapes, in zigzag fashion. So, it is very difficult to calculate exact area and exact currents, ratio of area to current. So, in that case you can assume that this is having an inductance, this portion, say side P and partial inductance, and this portion is assumed to have its own inductance, this portion another inductance. So, you are assigning to each piece of this wire that are orienting differently one inductance value. So, how you define this inductance value, that we will see in the next slide, but if you can define like this, you can calculate the total voltage drop across as V equals loop inductance times di by dt, and that loop inductance is nothing but now here the current is entering. So, the positive one. So, here the current is entering from the opposite side. So, LPP 2 times LPP, then LPR is between this and R, LQQ is this, LQS is between this and this. So, LPP and LR are the same. So, that is why you have the factor 2 over here, because in either way it is the same one. So, you get loop inductance times di by dt. So, you can write it in this way. Now, how do you find LPP, LQQ or LSS and LRR, which are the same? So, they are defined like that. So, if you have a current carrying conductor IA and some flux phi m, and assume that you have a imaginary return conductor at infinity, and if you can set up this expression LAA equal to phi m by IA and do a calculation, that is integral B dot ds by IA or integral B dot ds by IB for mutual inductance, then you get an expression like this. So, for self partial inductance, you write B is same as A and replace D by R, diameter by R, then you get for self partial inductance. So, this you can get from some of the electromagnetics textbooks, this type of expressions. Now, another comparison of inductance of circular and rectangular wires. For example, you have a long circular conductor in free space, so return is far away, and in the second case you have a long rectangular conductor in free space and return is far away, and long circular conductor and return close by. So, again from handbooks you can get these expressions for inductance value. So, let us do some numerical calculations on these values and see what kind of inferences one can get. For example, in the circular conductor D equal to 1 millimeter, very thin wire, you get L equal to 1.5 microhenry per meter. As a thumb rule, often you say that inductance of a wire is 1 microhenry per meter length, because the variation is logarithmic depending upon whether return conductor is close by or far. And if diameter is 10 millimeter, inductance becomes, because you have more surface area, and inductance becomes 1 microhenry per meter. But if you bring the return from infinity to close by, then you see that for D equal to 1 millimeter and return 4 millimeter away, inductance can be reduced from 1.5 microhenry per meter to 0.83 microhenry per meter. You can have a reduction by bringing close the wires together. It makes sense also, because when you bring close the wires together, the flux linking with that enclosed area is also small, because the area is small. Now, for the same thing with the rectangular conductor, here this is the expression for inductance and certain thickness, S is equal to 0.024, you get surface area, and inductance is 1.12. And to achieve that, you need a wire of diameter of 7.65 millimeter, that is almost 1 centimeter. It is very thick rod. You need that for achieving L equal to 1.05, whereas already close to that value you can achieve with a thin strip, which is very easy to realize. Then how to reduce inductance? As we have seen before, large surface area tend to reduce external inductance, and it is easier to achieve large surface area by strips or tapes rather than round conductors. However, reducing the length of the wire is more effective. So, here you have seen that by increasing the diameter to 10 for increasing the surface area, you achieve a reduction of only 0.5 microhenry per meter. But instead of 1 meter wire, if you can use 0.5 meter wire, already your inductance become 0.75, half of 1.5. So, reducing the length of the wire is more effective in reducing the total inductance than increasing the thickness. Then another measure is run the wire close to the ground plane, close to the return wire, that is reduce loop area to reduce induced voltages. So, this we have seen it comparing this picture with this one and the calculations below. So, rule of thumb, inductance of a conductor is approximately 1 microhenry per meter or 1 nanohenry per millimeter. Every millimeter reduction will reduce at least 1 nanohenry from inductance. 1 meter earth wire has about 126 ohm impedance at 20 hertz compared with less than 1 ohm at power frequencies. So, the importance of inductance cannot be neglected while finding the impedance under transient conditions, because it can have a tremendous effect. Now, capacitance of wires. You have two conductors of cross section, two parallel conductors, separation distance capital D, cross section is small d, and height is h. Now, you have a capacitance. If they are carrying voltages, you have a capacitance between these two conductors, you have a capacitance between this conductor and to the ground. So, that circuit is shown here. C12 is the mutual capacitance, Cr is the reference capacitance or capacitance to reference. Now, if diameter is 1 millimeter and h is infinity, and if so, you do not have the influence of the proximity of the ground, it is in free space. So, when d equal to 5 millimeter, capacitance between them is 12 picofarad per meter. Now, here you are introducing now a ground plane very close to these two conductors. So, just 2 millimeter away. Immediately you can see that the capacitance value reduces from 12 picofarad to 5 picofarads per meter. And if it is you increase the distance from 9.3 to 2, then 20 millimeter, 7.5 to 0.5 picofarads per meter. So, you can see that the ground plane has an influence in this mutual capacitance. So, in general, ground plane decreases this mutual capacitance between the two conductors. So, this is called the coupling capacitance. So, impedance of grounding wire. So, this impedance of wires are very important whenever we consider grounding. Say for example, if you have an equipment in an equipment rack, suppose you are asked this question, okay, you have two wires, a 60 millimeter square 1 meter wire, a 25 millimeter square 3 meter wire length. So, how you will use those to earth this? One may be tempted sometimes to say that okay, 25 millimeter square wire has a lot of thickness, so it can reduce the inductance and other things, but at the same time it has got larger length 3 meter. So, one can guess that okay, 60 millimeter square wire may be better, but let us do a calculation and see if it is really indeed true. So, this is frequency and this is internal impedance. You calculate R plus j omega L for 25 millimeter square 3 meter wire. So, it comes over here, then around this value 200 megahertz, let's say tan beta L, that is the impedance. It peaks, there is a resonance peak over there, and at around 500 megahertz there is a trough. So, likewise it goes, whereas this resonance behavior happens in a 60 millimeter square wire much later, only towards 700 of 600 megahertz it is coming. So, in this case surely you will be using 60 millimeter square 1 meter wire for earthing, so that you have much larger range of frequency for operation. So, this ends this particular module.